Go.
All right. Hello, everybody. Welcome back to our second recorded podcast. This is our third overall podcast. We had a YouTube live a couple weeks ago, which ended up being a whole lot of fun, a whole lot of interaction with the fans, if you call them that, maybe fans, students. But it was just a pleasure, and we've only scratched the surface of physics so far. Today, we're going to be talking about quantum physics, and we'll get into the difference between our previous topic with, things like gravitational fields, things like that, and then quantum physics in a moment. But first, again, if you're listening, please feel free to, subscribe to whatever it is platform you're listening on. And also, if you have any questions and you can't make the next live stream, which again, we're going to do a live stream about a week or so, maybe 2 weeks after each podcast. You can't make it, feel free to comment on whatever you're listening to. We'll pick that up, and we can always bring up some questions that you have in the live stream, even if you can't make it there or you don't want to comment, or you can't comment if you're working, who knows? I mean, if you're working and you want to watch, we're not going to judge.
And there's no such thing as a stupid question. All questions are good questions.
Indeed. Well, I haven't even introduced you yet, Lee. I apologize. I've been talking this whole time. I'm Josh. This is Lee. Hopefully you guys know that by now. So one more thing to mention before we get into the topic today. Since we're exploring quantum physics, we're going to be opening up sort of the format of this podcast a bit more to what-if questions and theorizing and using our imaginations, you could call it. And again, that just goes, it goes along with the fact that this field is so fascinating and intriguing. You're only going to be able to ask what-if questions anyways. But also, it just lends to making physics incredibly fascinating when you can ask these what-if questions based on these new concepts that you're learning. All right. So anything else to add, Lee, before we jump into it?
I think you covered it all, Josh. Thanks.
Sure. All right. So like I mentioned, quantum physics today. Let's start off with, what is the difference between what we studied last time, which I guess big things, right? So gravitational fields, black holes, massive things. And then what we'll be studying today, quantum physics.
Well, you kind of hit the nail on the head there. The last time we studied gravity, which for the most part it governs all particles, but we use it to see what happens to very large objects, planetary and astronomical sized objects. Quantum mechanics is the exact opposite. What happens when we get very small? How small can we go, and do really small particles behave the same way that really large bodies of mass do? Spoiler alert, they don't, but I won't give away much more than that. And I think the theme here is that the universe, as quantum mechanics will show, it's not as tangible and concrete as we think it is. We think about things in very discrete pieces, locations as being exactly where they are. This is 2 blocks over, this is 18 feet over. That same logic does not apply at the quantum level.
Okay, great. So I was just thinking of a question, which is probably getting a bit ahead, but it is fascinating that what happens on the small level, the tiny level, does not reflect what happens on a massive level. And I wonder, maybe I'm getting ahead of myself, but I wonder, is there another field of physics that tries to study the link between the two? Between the change between those two fields?
Great question, Josh. This is part of why we started this podcast, is to think about what do we notice in the gravitational realm and singularities, and what happens at the quantum level, and is there a way to reconcile those two? And there are many different fields. Loop quantum gravity, there is string theory, there's a number of other things to incorporate the standard model, which is what we know happens on most things except for quantum mechanics. So that will be probably one of our later series podcasts, is to discover what theories try to bring these two together.
Okay, great. That's good to know. Yeah, string theory will be coming up a little bit later on. So quantum mechanics, can you give us maybe a quick summation of first what is quantum mechanics, but also how did it arise? I know it's relatively recent in the modern era, but what did it arise from, and what is it exactly?
Yes. So, up until the the 1800s, we had this classical view of physics, and that was that everything sort of would lay on this continuum, right? We would have people, and you and I could be any number of distances from, point X to point Y, and an infinite amount depending on how we moved our body. And so that was considered the sort of classical view. And we had the same view of electrons and particles that they can pretty much be whatever energy. And it wasn't until de Broglie discovered the fact that there were quantized energy states. So that's where quantum came from. It's like, so actually when you look in the really small scale, energy many times comes in these little packets. So if you look at an electron, it can't just be any energy. It's got very specific energies. Same thing with a molecule or an atom. They have very distinct states, quantized states of energy. And so that really was what birthed quantum mechanics, is studying things. Why are these things quantized? What happens at the very small scale? And this was very controversial when it came out. I mean, a lot of these theories were, when Einstein came out with special theory of relativity, when de Broglie came up with this, Born came up with his theories. They were very controversial because it just seemed very counterintuitive. And it still does, as we'll discover today. Quantum mechanics is not an intuitive form of physics.
So going back to what you mentioned about the energy with electrons, now, and molecules as well, is this always the same energy, or the different types of energy? And why, I guess I'm not fully understanding, why would it be so radical if like we take an electron can only have a certain electrical charge? Is it because it throws off the prediction of it?
Yeah, I guess, maybe it's, so, but before that, also the idea of charge too, right? That was not like, we just thought, things are positive or negative. There's some amounts. Now we know, things have a plus and minus charge. It's how many more electrons than protons do you have, or how many more negative particles than you have than positive particles. So even that view that like the atoms were quantized and there's very discrete spaces was also, that was very foreign to us at the time. So that's probably what made it very controversial. And the study of it also is, just as we started to wrap our heads around it, it just kept getting weirder and weirder. It's like, this new thing called photons, they're waves. Okay, all right. So, how does a wave act? I'm used to billiard balls, right? Like electrons bounce off of things. And then they said, well, no, sometimes they're particles. And then it's like, wait, they can't be both. It has to be one or the other. And then we realized all these particles, they can act as a wave or as a particle. And so that, again, just the more we started to study it, the more our eyes were opened to the uncertainty of the universe.
Yeah, that's fascinating. So going back to the wave part of it, do you know how they first discovered that, or what even, like, how do you even make that sort of discovery, going from just thinking of things as particles with billiard balls to putting it on like a wave or a frequency chart, basically?
Gosh, I should definitely do more research on this. You asked me a lot of historical questions. For a physicist, my physics history is terrible. But what some of the early experiments were looking at things, looking at photons as they travel to and around objects. And so you can imagine that, like, if you have a little airsoft gun with a ball in it, you shoot something, and it either, if you're like trying to shoot through a hole in a target, it'll either go through the hole or it won't. And if it goes through, its trajectory is going to remain unchanged. What they noticed with photons is they didn't do that. There's a lot of astronomical phenomena that we can see, that when an object, if you shine a flashlight from behind an object that's covering that light, the light still makes it around. How does it go around, right? Like, you can test this sort of experiment. I mean, it's if you put a flashlight, let's say of diameter 2 inches, and you put a 2-inch diameter cover over it, you'll still see a little bit around the outsides, and that has something to do with called parallax, which is basically light bends around things. So
Hmm.
that's the idea, that it behaves as a wave.
Okay.
Same thing as it's going through something. We understood that like it's acting as a wave. But then there were other experiments called, like there's an experiment called the photoelectric effect, where they recognized that light was also a particle. You could measure, it would hit something and it would deposit a certain amount of energy. And so we'd say,
Right.
oh, okay,
Like a
well, that was
tan.
a particle. Huh?
Like a tan.
Like a tan, right.
Yeah. Wow. Okay. So then, from the beginning here, it was basically light itself that kind of led to this split, or this new way of thinking about physics.
Yes, it was later expanded. Again, somebody can correct me wrong. It was later expanded to realize that it's not exclusive to photons. And if we recall from last podcast, photons are the force carrier for the electromagnetic force.
Hmm.
So they're the particle that transmits the electric force. If you see light in the room, that's it. If you've ever gotten X-rays, those are photons. Radio, if you listen to something on the radio, those are photons as well. So photons come in many different parts of the spectrum, visible or not.
Okay, I didn't know that. So radio waves are also photons as
Yes.
well. Oh.
So they travel at the speed of light.
Oh.
Yeah.
Okay. But you can separate them out from light, or is light always have radio waves in it?
It's really interesting when you think about it, it seems like they're two very distinct things, right? Like we see light and we don't see radio
Is
waves.
that the particle and wave though thing? Like the difference there again?
Not
No?
really.
Okay.
They're both, they're both particles and waves, but
Hmm.
like they're just, the electromagnetic spectrum goes from the very low end, which is microwave, and radio. Sometimes we think of microwave as dangerous because it heats stuff up, but that's just because microwaves oscillate at the resonant frequency of water. So the energy in
Hmm.
microwaves is not that high. So at some point, like if you had a device which you could change the frequency of photons, you wouldn't see anything. And then all of a sudden, at a very narrow region, when you get to about 400 nanometers, you'd start to see it turn red, and then it would go through Roig Biv, and then it would end up being blue, and then it would turn into ultraviolet light, and then you can see a little bit of ultraviolet light, and then you stop seeing it as it goes into extreme ultraviolet, X-ray, and gamma rays. Pro tip: if you have that and you have the gamma rays turned up, turn it away from you. They're pretty dangerous. Actually, don't turn them at anything, because they will essentially obliterate anything that comes in front of them.
Oh wow. Okay. That is fascinating. So the whole spectrum provided did well, again, I'm asking another history question. If you don't know, you don't know. But did we know about like radio waves before we discovered this?
Yeah, funny
Okay.
enough, we did. We had known that. It wasn't until later that we discovered they were all part of the electromagnetic spectrum.
Hmm.
But that's, as physicists, you observe something and you say, oh, we observed this phenomenon that we can, if we move these two pieces of metal together, we can get them to send this sort of weird signal, right? And then we see light, but that's different. Those are
Hmm.
those are little particles hitting our eyeballs. We never put two and two together, that those particles hitting our eyeballs are actually waves also.
Wow. Okay. Yeah. So spectrum. That's fascinating, and it's crazy that it's light itself that once we started studying that, we discovered all this, right? Because light itself illuminates things. When we see things through light, and then by light and by studying light itself, we discovered all these crazy new theories that have led us to today.
Yeah.
So speaking of that, going off of sort of quantum mechanics, what we've discussed so far, how does that relate to Einstein himself? Because I know you mentioned a couple, Einstein and the other guy, I've already forgotten his name.
De Broglie and
De Broglie.
Born,
Okay,
yeah,
and Born.
Max Planck, they were all innovators. Like you can look at an easy way to find out who made major leaps and bounds at this time is look at all of the universities in Germany, and it's like, oh, the Max Planck Institute, the Max Born Institute, right? They all got institutes named after them. So anyway, last time we talked about Einstein's general theory of relativity, which determines how we interact with gravity. Funny enough, before that, Einstein had developed the special theory of relativity, which governs how light interacts and what we can expect. And he at that point basically determined that there was a speed of light. There was a fundamental speed limit of the universe, and that was the speed of light. Nothing could go faster. So sort of like the what if I think about when I think about what came out of this is like, what if every answer you had to give was it depends? And that's what discussing the speed of light yields. It all depends on the observer. So in thinking about the speed of light, it's probably important to think about it as like, what is it? We think about it as a speed limit, but it's not like, all of a sudden let's say we could create the spacecraft and like we would just gun it and think, okay, well at some point it's just gonna, it's immediately gonna stop accelerating. We'll just hit that speed limit. In practice, that's not how it would happen, and that's not how it happens when you think about particle accelerators. When you look at particle accelerators like CERN, biggest one in the world, the particles never get to the speed of light. They get close. They get 99.99%. But one way to think about it is if we created a spaceship, let's say it ran on gas. And I said, well, we're going to need a lot of gas for this. We're going to need 100 million gallons of gas, and we're going to get to 90% the speed of light. You'd think, oh, that's great, awesome, okay. And then you'd say, well, what do we need to get to 91%? I'm going to say, oh, actually, we're going to need all the gas on Earth. We're going to need 100 trillion gallons. And you'd say, oh, okay. And you'd say, well, what about to get to 92%? It's like, we're going to need all the gas in the universe. So at some point, when you're trying to get to the speed of light, the particle requires exponentially more energy to get there. So you would essentially just be accelerating slower and slower as you ran out of energy in whatever device you're doing to try to accelerate a particle to the speed of light.
So is that similar somewhat to confidence intervals, where like the higher you get up, the more of an outlier, the more rare it is to occur? So like if you get to 99% of the speed of light, you're taking up so much energy, whereas if you're just at the middle, you're not taking up that much energy.
Yeah, that's probably not, I mean, there's some differences in it, but that's probably a fair, rough analogy to think about. The particles that do make it to very close to the speed of light require so much energy that it's very rare. There's not many that aren't man-made or don't happen from major astrological events.
Okay.
Astronomical events.
So would you say it's near impossible to create light itself? I mean, obviously we can create like a flashlight, we turn on the light, but to create light make something, yeah, go ahead.
No, I was going to say, great question there. So photons are different. So what makes it difficult to accelerate particles and to accelerate mass is that you have to, the mass requires, the E equals mc squared requires requires energy to get us to that speed of light. Photons don't have any mass, so they always travel the speed of light. They don't go slow, they don't go fast, they always travel at the speed of light. Now, there is some interesting pieces. If you're looking at light as it goes through materials like glass, it does from a certain reference frame look like it's going slower than the speed of light. There's something called the index of refraction that determines how much slower it's going to go. But it depends on the observer, basically. This is going to be my explanation for all of this. So photons always travel at the speed of light. Anything with mass requires some energy to be able to get there.
Okay, so there's really no mass that could travel the speed of light that we know of, or is, yeah, okay.
Yeah, now there is, so, there's always interesting sort of outliers. There are these particles, gosh, I think they're called muons.
Muons, okay.
They're particles with mass that can travel at near the speed of light, and they can go through objects faster than light can. So they can move through the objects faster than a photon can, but that has to do with the way that a photon interacts with it. So in terms of it still doesn't go faster than 300 million meters per second.
Okay, but it goes through something faster than light would go. It
goes faster than a light particle. Yeah.
Because light slows down when it hits some kind of mass at some level. Okay.
Yeah.
Okay, that makes sense. Well, as much sense as it could make, I guess. uh, okay, so what does light? Is it that light is a wave and a particle that led to this sort of like it depends on the observer kind of thing? Like, was there some kind of link there that led to this quantum mechanics, or what was it
Um,
exactly there?
yeah. So I mean, I think the depending on the observer piece is one thing. There's a lot of like interesting scenarios you can paint where you can say, okay, well, Josh, you and I are going to give a couple laser beams to my cat, right? We'll have my cat shoot laser beams in both directions, and then we'll
Okay.
have a little flag target on each side that says, oh, when does the light particle get there first? So if all three of us are sitting there, if they're equally spaced, we'll see, okay, well, the flags are going to lift at the same time. If you start traveling away from us, you're going to see or let's say you start traveling towards the target on the right, you're going to see that flag flip up first. If I transfer the other way, I'm going to see the other one flip up first. So in our own reference frames, we're all going to see the flags go up at different times, but they're all still going to be right. And it just has to do with the fact that, one example of this is imagine that we're in a really fast car. We're in a car that goes 90% the speed of light. You asked a little bit of this last time. If I shine a flashlight out the side, is now the beam going 90%, like let's say 100 million miles an hour plus 300 million meters per second, right? So now is it breaking the speed of light? No, because the speed of light's always constant. So that's what dictates this difference in observers. So that phenomenon was very difficult for people to handle, and that's what Einstein covered in his special theory of relativity. The wave-particle duality came after Einstein's study of special theory of relativity, as we grappled with trying to think of, I mean, it's either a particle or it's a wave. It can't be both, right? We're still thinking classically that, you're not a cat and Josh, right? You can either be a cat or you can be Josh. One of them has a much better life than the other. Spoiler alert, probably cats. They have great lives.
Yeah.
So the wave particle duality started with a very simple experiment that's been redone in every physics lab. That every physics lab still done to this day, and it's called the double-slit experiment. So basically, the idea was that if it's a classical particle, let's say you shine a flashlight through a little rectangle, or let's say you shine it through a star shape, and the whole thing's covered. If you look on a screen in the back, it's going to look like a star, right? That seems pretty natural, right? The screen is going to block anything. The covering is going to block anything that goes through it, and the star opening is going to let photons go through. What they did is they said, well, imagine, let's put two of those star-shaped emblems next to each other. Let's say we put one star and one square emblem next to each other, really close. This is sort of the double slit. Then you would expect, if it's classical, what would happen is on the other side, you would see a star outline and you would see a square outline. But that's not what happens. What you see is a series of dark and light spots on there, similar to what you would get if you ever look at like tidal waves in a pool. If you have a plexiglass container, you can see that with two people drop an object in on opposite sides, the waves interfere with each other and you get troughs and crests of those waves. So the same thing you get if you put two slits next to each other. So you say, oh, okay, so this is definitively telling us that light is a wave. So we weren't really happy with that. It still didn't sit right. So
do you know if the original was that on purpose? So they wanted to put those two slits together? Was it by accident? Like did they have an inkling?
Purpose.
So they were like
they were at that point. They're trying to figure out whether we know that Einstein had proposed that light can travel. That light was a particle. We had also found that light could sometimes travel as a wave. We had seen it bend around it. So we're trying to reconcile these two. So then what they said is they said, okay, well, let's imagine, we want to know how do the particles interact? Which particles interact with which ones, right? Is it always one from the left and one from the right? So what they did is they said, okay, well, what we're going to do is we're going to measure, which particles entangle. You can use these things called polarizers, right? Our sunglasses have polarizers on it because, sort of sidebar, the reason why sunglasses work is because when light is reflected off of the ground or reflected off of an object, only a certain polarization is maximized, sort of any polarization that is horizontal to the ground. And so sunglasses basically just say, we're going to block all polarizations that are horizontal to the ground. Some of the light still gets through, obviously, they don't work perfectly, but it blocks enough of it that, that it works. So we're going to do the same thing.
Quick question here. Yeah. This might sound dumb. What exactly is polarization?
Not dumb. It's a great question. Polarization is which way the electric field is wiggling. So when light propagates, it does propagate as a wave, and you have these intertwined electric and magnetic fields. And so if we look at, they can be any if you think about it coming straight at you, it's wiggling sort of, either left and right, and then that can go anywhere along the axis. So polarization is basically just saying, hey, where is it oriented, right? You could imagine that, like, if we look straight up, it's like, let's call this 0 degrees, and let's go fully around the circle, full 360 degrees. So, so polarizers on sunglasses take out anything that is 100 parallel with the ground, basically.
Okay, that makes sense. Cool.
So back to the double slit experiment. So we want to figure out which ones, which photons are interacting with which ones. And so we're going to put an up and down polarizer on the left, and we're going to put a left and right polarizer on the right. That way, on our screen, we have these special screens where we can look at which particles were polarized left and which particles were polarized right. And so this will tell us, okay, cool, we get to see which ones are mixing, which ones are interfering. As soon as you do that, it stops showing an interference pattern. It goes back to, now it's just a star shape and just a square shape. So it goes back to just a particle nature of it. It's just going through the slits and they're not interfering.
So if there's some outside force, in this case, some kind of polarization on either side, then whatever weird thing is happening stops and everyone kind of straightens out and behaves. It's like a parent coming home.
Yes, it does have an analogy to, what we do in our everyday life. If I asked you to try to solve a math problem on your own, let's say this certain math problem takes you 2 minutes. If I sit there and watch you from behind, it probably will take you longer, right? I'm changing the way the system is interacting. And so the fundamental nature of quantum mechanics tells us that by measuring a system, you are disturbing it.
Which is, I do think it's pretty, I would assume that was really stunning because, like, it makes sense if you're watching me take a test, I would do a little bit worse perhaps because I'm nervous. But if you're just sitting there observing things that aren't alive, right, that are apparently just supposed to do the same thing every time or live by the same rules, but then suddenly they start acting differently, it's almost like they're alive as well in a way.
Yeah, it's really weird. You think, how do they know they were being measured? And so we thought, okay, well, it actually kind of makes sense, right? We're changing, we're only selecting certain polarizations and then they can't interfere. So, okay, that makes sense to us. So we decided to get a little trickier. And we said, okay, well, what we're going to do is we're basically, after it goes through the slit, each of the various slits, we're going to put, you can put these certain crystals, which will create a coherent pair. And so, not a coherent pair, a superimposed pair. Gosh, I did the same thing. An entangled pair. Sorry.
Entangled pair. Okay. Wait, what do you mean by crystals? What does that mean exactly?
Like any sort of like lattice structure. So they call them BBO crystals. It's essentially just, consider it kind of like a gem, right? So that what it does is they call them frequency doubling crystals. So what happens is you can send in one blue photon and you'll get out two red photons, because a blue photon is, let's say 2 MeV of energy, and a red photon is 1. So you can take 2 unit of energy and you can make 2 ones, right?
It's like a converter, basically.
It's a converter, yes.
Yeah.
It converts it to 2 identical, but once you do that, they're entangled. And entanglement really is where the interesting part of quantum mechanics comes into play, because once they're entangled, you can't, like, what the knowledge of one affects the knowledge of the other, and that's what we learned from this experiment. So
wow. Okay.
Yeah, what we did here is we said, okay, what we're going to do is, after it goes through the frequency doubling doesn't change anything. The creating the entangled pair doesn't change anything. So we're going to create a pair, and then we're going to send one of them to the screen, and then we'll detect the other one. So we're going to detect the polarization in the other one.
Sorry, real quick. So these photons or particles only become entangled if they're converted, or can they be entangled? Like
there's other ways you can entangle that. That's just one method. You can create entangled photon pairs. They're created naturally. Anytime you have, you can basically have particles that annihilate to create. There's other processes that can create entanglement. This is just the easiest one for us to reproduce. So obviously, when you do that, you think, okay, what I'm really doing is I'm creating a copy of this photon. That way I can measure it in one place and watch the interference pattern on the other. So, they had this setup, and as soon as they turned on the detector to detect the photons, they stopped showing the entanglement pattern. So this is when it really gets spooky. So if you don't detect them, let's say the right side, you just send it into a black box and you never detect it. It will show the interference pattern. As soon as you turn on that detector, then it stops showing the interference pattern. So it's almost like the photons that are going on the screen that we're watching know that the entangled pair got detected, and they said, okay, now we have to act a certain way. And that still didn't sit right. So then we thought, okay,
wait, real quick. So in that case, if you're observing one of them, nothing happens. You can still see the interference. But so if you just observe one of them, it would.
Imagine it splits off to the left and the right. The left hand goes to a screen that we're looking at with our eye, and the right one goes to a detector.
Sure.
And that detector, you could turn it on and off. Let's say.
Okay.
As soon as you form the act of detecting the entangled brother, the sister knows, and she stops showing the interference pattern.
Okay. So you'd have to detect the other one in order for that one to stop showing the interference pattern.
Yes.
Okay.
Right. And they did this. They did something they got very sophisticated, because it was not making sense. So they did something called the delayed choice quantum eraser, which is basically like saying, okay, we're going to really fix this once and for all. We're going to have one of them hit the screen very early, and then a mile down, we're going to detect it way after. And it still didn't change anything. So then, you just have to be faced with this fact that, okay, these two particles are entangled, and the instant you measure one, the other collapses into a state. And what we gather from this is that there is something called a superposition of states, right? When you create this entangled pair, this kind of goes in the idea of quantum computing, right? Standard computing is a bit is either 0 or 1. A quantum bit is one where it could be 0, it could be 1, or it could be both, right? So you have this entangled pair of states. And so that's essentially what happens to all particles, is they are going to be a superposition of all of the states, unless you force them to collapse onto something, unless you observe that they are one thing. They will always stay both of them.
Do they go back to being entangled if or interfered if you stop observing them
Hmm.
or stop observing one of them? Okay, so it goes back to its normal state.
Yeah.
It's almost like a like a cartoon where like there's like chaos going on in a room that's dark, and then the mom turns it on, and everyone's sitting there nice and proper, and then she turns the light off again. Just everybody's going crazy and acting wild. It's like as soon as you're observed by your parents or something like that, then you behave, but otherwise you could act crazy.
Yeah, and there's also this. It kind of ties into the speed of light because it seems weird. Like let's take all of the physics language out of it, and let's imagine that like what we can actually do is we can create two cubes, okay, and we can send, and these cubes can be either if one is red, the other one's going to be blue. But
Okay.
like you sort of hide them, okay? So you mix them up, you don't know what they are, and you shoot them off at the speed of light. You don't know which one is red and which one is blue. The instant you measure one as red, the other one will automatically be blue. The instant you measure one as blue, the other one will automatically be red.
But if you
And
measure it as something else, nothing will happen.
nothing will happen.
Okay.
It'll be completely,
It's like a code.
yeah. So the weird thing is, like in that example, if you send them off at the speed of light, it's almost like you could transmit information at twice the speed of light because you have the speed of light going in one direction, the speed of light going the other direction.
Hmm. Now, is this um, only found with two particles, or can you do it like four, where you suddenly have four particles that all act in the same way?
Entanglement happens in pairs.
Okay.
They have tried to, they've tried to couple more, but naturally it happens in pairs.
Wow. That's amazing. That really is cool.
It's really
Weird.
just, it's very, very bizarre that, it is something, it won't, it won't be, it won't be shown unless it has to be, right? It fights our classical view because, if I have a red cube, it's always been a red cube and it will remain a red cube. There's no way it could be a blue cube if I look at it later.
Hmm.
To me, we could certainly do another podcast on this. This reminds me a lot of like in video games, when you're playing a video game like a first person shooter or something, the game doesn't render anything behind you until you observe it, right? So it's almost like it's almost like a simulation, right? Like nothing is going to get rendered unless you need it to be. So it's some way of sort of like saving the data of the universe. It's very odd.
Hmm. Yeah, it's very strange. So again, no matter where or how far apart these two particles are, space doesn't matter. Um, this doesn't really make sense, but I guess you still like time is still the same, right? So there's no way you could try and test one particle and see if it changed in the past as well. I guess it's kind of a dumb question, but like because space has now been kind of transcended with these particles, but I guess it's still beholden to time. Like it's only in the present moment are each one's changed, right?
Yeah. Well, so that's a really good, that's a very interesting thought. So yeah, if you and I were creating an experiment, let's say that we have this sort of entangled pair that's just shooting it off in opposite directions, and you and I sort of step off from this emitter. We step off 10 feet, right?
Mm-hmm.
Like if I measure red, you measure blue, right? Let's say that you continue to step off. You keep stepping and stepping and stepping.
Mm-hmm.
Um, you know, if you measure, if I measure red, you can be certain that you're going to measure blue. But if I don't measure it at all, then then you still have the possibility of measuring either one, right? That's sort of the weird thing about it is as soon as I measure, you don't really have to measure, right? Like I always know, like, hey, yeah, I got red, you got blue. But if I don't, then I know that there's a 50-50 chance that you're going to measure red or blue. So
Okay. Well, that's similar to like with formal logic, right? I'm an LSAT tutor, Claiborne and all that. You have if-then statements. So let's just say if I'm hungry, I'm going to eat food. So the if statement is sufficient to guarantee the next statement after then. So if I'm hungry, it always guarantees the fact that I'm going to eat food.
Yeah.
But if I just had the statement, I'm going to eat food, that didn't guarantee anything. It doesn't mean that I was hungry per se. It just meant that I'm just eating food. I might not be hungry. I might just be eating because I'm bored or whatever. But with that measurement part, like if you measure it red, it's going to have to be blue for me. But if I measure it, it didn't have to be red for you necessarily. You might have measured it, you might have not.
Yeah. And it seems like, up until, I don't know, maybe a couple dozen years ago, it just seemed like this was a cool thing for physicists to discuss. And it's just like, oh yeah, this is cool. Yeah. So what? Now we know that we can make quantum computers out of this, right?
Mm.
We can make these things called qubits, which is exactly what I said before. It's a superposition of states. It can be 0, 1, or both of them.
Okay.
You know,
And is it only both of them if you're not measuring them?
well, yes.
Okay.
So there's some sophisticated ways you do it when you're doing it with a quantum computer, but they're all valid states. You can be 0 or 1 or both. So that is, that's what they're using to make quantum computers. And, to try to understand why, there's a big race to make quantum computers, to make quantum networks right now. And you may think, yes, so what? Why does it make a difference? It's okay, great. You can do 3 instead of 2. But if you think about how processing power and how memory and all that works, everything happens in powers of 2,
Mm-hmm.
right? So this is why if you buy phones, it's like, oh, why is it 16 or 32 or 64 or 128? It's like, oh, because those are base 2 systems, right? It's just 2 raised to some power. If you start to do 3 raised to some power, you start dwarfing, powers that base 2 systems become obsolete after like a couple of iterations, which is good and bad. One of the downsides is that our encryption systems are based on 1024-bit encryption, which is like numbers so large that there's no way you can randomly come across it. But if you have a quantum computer, a very weak quantum computer could break the encryption of our network very quickly, because it doesn't require near the amount of processing power. Now, in order to sort of brute force through an encryption, you have to have a supercomputing network to go through all the possible iterations.
Okay. Yeah, I mean, the 2 to 3 makes sense. Like if you just think about 2-dimensional space, everything is flat, and then you just do one up, you go 3-dimensional, suddenly like all of life has a new element to it. So going from 2 to 3 in terms of math or in terms of exponential makes a lot of sense. How I mean, would the computer still work the same way? It's just you're adding a third option into it. Like how exactly does that work? Do you know?
Well, there's some like practical implications to implementing a quantum computer, but there's that. It sort of depends, right? Our entire everything we do electronically is based on a base 2 system. Like things are sent in bits of either 1 or 0. So this changes the entire structure. So you could have a quantum computer that's working really fast, but you would still need to transmit data over a network that's base 2 systems, a sort of classical network system. So in order for us to really take advantage of quantum computers and quantum transmission, quantum networks are also a thing, and thinking about how do we change the sort of data transmission structure to account for now this factor of 3. So it's not trivial, but it is something that we're working on.
Yeah, it sounds very revolutionary, even amazingly enough, even though computers themselves are revolutionary not too long ago.
Yeah.
Wow. Okay. So that's one sort of practical aspect of this discovery. Have there been any other ones in terms of other types of technology with quantum mechanics, or has it mainly just been this new discovery of, oh, we could do both as opposed to 0 or 1 with binary?
Yeah, I mean, I think I mean, in terms of taking advantage of quantum mechanics, I think that there's, certainly, applications of things like lasers probably take more advantage of special relativity and light propagation than they necessarily do for quantized states. But yeah, there's been, I guess there's, when you think about what happens in the medical field, a lot of that is probably more nuclear based, so it doesn't enjoy the same effects of quantum mechanics. Quantum mechanics is essentially just understanding that state, and understanding things at a very small level helps us with things like nuclear physics, because nuclear physics to some extent obviously depends on what happens at the very small scale. So MRI machines depend on nuclear magnetic resonance.
Okay. Yeah, it's fascinating because if you take those discoveries and you put them into sort of ancient philosophies and religion, even you've got something like Taoism, which I think I have this right, but you've seen that circle with the in the middle, like half is white, half is black, and then there's a dot of white in the black, and then there's a dot of black in the white. And again, it's that there are two different things that always exist, and they always will exist, and there's always a bit of each in each one. It's fascinating how you can discover those types of things within the very fabric of reality, but it matches up very closely to what people might have already somehow, I don't know how they discovered it, but they somehow discovered it irrespective of, of physics, basically.
Yeah. I guess another thing is atomic clocks. The ability to tell time with increasing accuracy is like, well, why do we need to really know it? We probably use that every day because GPS systems are based on very accurate clocks to determine our position, because it depends on how long the light, or sorry, the photons travel from the satellites to us to help us triangulate our position. So that's probably another application. So some medical applications, devices is probably the biggest application of using quantum mechanics for our benefit.
Wow. Okay. So I think that might be a good place to start wrapping things up there, because this is quite a lot to take in. I'm sure there'll be a lot of questions about this concept. Yeah, it's mind-blowing in a way. So are there any other sort of things that you want to tie into this, or that you feel we hadn't covered yet about wave-particle duality?
I think this was pretty heavy. I think it's important to know, and maybe we'll add a little comment at the beginning, that this is part one of a two-part series on quantum mechanics. The next time we meet, we're going to discuss the uncertainty principle and some other quantum paradoxes. So yeah, I think we've covered about as much as our brain can handle for this podcast.
Yeah, it's a very heavy meal. We have to digest it now and see what we can learn from it. But that is fascinating, man. It really does. Yeah, it's crazy. It's crazy. I mean, in many ways, it's similar to like sort of anecdotes you hear about, like a twin who his twin died halfway across the country and he immediately knew something had happened, right? Things like that.
I think that's, that's part of what we strive to try to come up with some analogies and some practical applications. Those, I've always thought those are interesting. I love like theories, things.
Mm-hmm.
I've always thought I had this theory that neutrinos could entangle coherent information with neurons in your brain, and neutrinos go through us a million times a second. So maybe a neutrino goes through, entangles some information from my head, then entangles it in your mind, and that's why sometimes like I just had that exact same thought, right? That's the part of me that wants to believe that there's some other sort of crazy theories out there. The practical side of me says, statistically speaking, what are the odds that like two people are just going to have the same thoughts? How many times do we expect that to happen in a given lifetime? And that's probably a more rational way to look at it, but it's not as fun.
Right, exactly. Well, why not both? Both could be correct, right? As we've learned, it doesn't have to be either or in this case, per se.
Wow, yes, that's the whole point of this, Josh. You're right.
Indeed. Well, okay, this has been a lot to chew on. Really interesting stuff. again, we're going to have a YouTube live. We haven't figured out the exact details yet, but probably about a week and a half or 2 weeks from now. So if you're listening now, if you're thinking of questions that you had during this, feel free to tune in. We'll make sure to advertise what the time is. And again, this is part one. Next time, like Lee mentioned, we'll be going to some other aspects. But yeah, it's been a pleasure. Any last things to add, Lee?
Nothing. Just if you have any questions, pop them in the comment lines of wherever you're viewing, and we'll post the link to the YouTube live in this video.
Make sure to subscribe if you're listening. But yeah, otherwise, thanks for listening, everybody. Enjoy the rest of your week/weekend whenever you're listening to this, in the future, in the past, or whatever space on this planet. Enjoy. You guys have a good one.
Bye.